Hello and a very warm welcome to today's session. I'm Rashmi, working as Assistant Professor, Department of Physics. In today's session, we will be looking at origin of induced EMF in a conductor moving in a magnetic field. In the previous session, we saw when a charged particle moves in a magnetic field, it will experience a magnetic force. So let us start with that. Have considered two magnets, and these are the two magnets, and have placed it in such a way it produces a uniform magnetic field between the gap. Okay, so this is the magnetic field which is uniform, and the strength of the magnetic field is given by B, and this is the magnetic field vector B. And I've considered a unit positive charge which is moving in, the charge is moving in this particular direction with a velocity v. Now what will happen to this charge? We know that whenever a charge moves in a magnetic field, it will experience a magnetic force, right? Now ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಯೂನಿಫಾರ್ಮ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇರುವಂಥ ರೀಜನಲ್ಲಿ ಒಂದು ಪಾರ್ಟಿಕಲ್ನ ತಗೊಂಡಿದ್ದೀನಿ. ಆ ಪಾರ್ಟಿಕಲ್ ಏನಾಗ್ತಿದೆ, ಈ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇರುವಂಥ ರೀಜನಲ್ಲಿ ಮೂವ್ ಆಗ್ತಾ ಇದೆ. ಈ ಮೂವ್ ಆದಾಗ ಚಾರ್ಜಿಗೆ ಏನಾಗುತ್ತೆ, ಆ ಚಾರ್ಜ್ ಮೇಲೆ ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ಬರುತ್ತೆ. ಆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ನ ಯಾವ ಥರ ಬರಿತೀವಿ? ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ which is acting on a moving charge is given by the equation Fm is equal to Q into V cross B. And the magnitude of the force is given by the formula QVB into sin theta, where theta is the angle between velocity and the magnetic field vector, right? So theta is the angle between V and B. And how did we find out the direction? The direction of the magnetic force which is acting on the moving charge was given by right hand rule. So using right hand thumb rule, we can find out what is the direction of force. So what will be the direction of force? The direction of force will be in the direction of the vector product V cross B. So where will be V cross B? For that we use right hand thumb rule. So right hand thumb rule states, if there are two vectors, in this case there is a vector V and there is one more vector B. And if I take the cross product V cross B, that V cross B will be in a direction perpendicular to the plane containing both V and B. So which is the plane containing V and B? Let me write the axis here. Say B is in x-axis, right? So here V and B are in xy plane. Therefore, the magnetic force will be in the z-axis. So this is the direction of V cross B. And the magnetic force will be in the direction of V cross B. So this is the direction of V cross B. So this is how we found out the direction of the magnetic force acting on a positive charge, right? So I had assumed this has a positive charge. Therefore, the magnetic force is taken to be upward. What if I take a negative charge? So ನಾವು ಈ ಫೋರ್ಸ್ನ ಡೈರೆಕ್ಷನ್ನ ಹೇಳಬೇಕಾದ್ರೆ ನಾವು ತಗೊಂಡಿರುವ ಚಾರ್ಜ್ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಆದಾಗ ವಿ ಕ್ರಾಸ್ ಬಿನ ನೋಡಿದ್ರೆ ವಿ ಕ್ರಾಸ್ ಬಿ ಅಪ್ವರ್ಡ್ ತೋರಿಸುತ್ತೆ, ಹಾಗಾಗಿ ಫೋರ್ಸು ಅಪ್ವರ್ಡ್ಸ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಅದೇ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಬದಲು ನಾನೀಗ ಒಂದು ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ತಗೊಂಡ್ರೆ, ಇದೇ ಕೇಸಲ್ಲಿ ದಿಸ್ ಇಸ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ದಿಸ್ ಇಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಮೋಷನ್ ಆಫ್ ದಿ ಚಾರ್ಜ್. ಆದರೆ ಇಲ್ಲಿ ಡಿಫ್ರೆನ್ಸ್ ಏನು? ನಾನು ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಬದಲು ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ತಗೊತಾ ಇದ್ದೀನಿ. ಆಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ಯಾವ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಇರುತ್ತೆ? ಅಗೇನ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ವಿಲ್ ಬಿ ಇನ್ ಅ ಡೈರೆಕ್ಷನ್ perpendicular to the plane containing V and B. So perpendicular direction ಅಂದ್ರೆ this will be the perpendicular direction. ಆದ್ರೆ ಈ ಕೇಸಲ್ಲಿ V cross B ನ ನಾವು ನೆಗೆಟಿವ್ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ತಗೋಬೇಕಾಗುತ್ತೆ. ಸೊ ವಿ ಹ್ಯಾವ್ ಟು ಟೇಕ್ ದ ರಿವರ್ಸ್ ಡೈರೆಕ್ಷನ್. ಸೊ ಇಫ್ ದಿಸ್ ಇಸ್ ದ ಡೈರೆಕ್ಷನ್ ಫಾರ್ ದ ಪಾಸಿಟಿವ್ ಫೋರ್ಸ್, positive charge, the force will be in the opposite direction in case of a negative charge. So the force in case of a negative charge will be in the opposite direction, which is minus z axis. So this is how we used to find out the direction of the magnetic force. So instead of using right hand thumb rule, we can also use Fleming's left hand rule. So what is Fleming's left hand rule? Fleming's left hand rule states, if you stretch the three fingers of your left hand, first three fingers of your left hand, such that the forefinger directs the magnetic field, the middle finger is showing you the direction of motion of the charge, then the direction of the thumb gives us the direction of the force. ಅಂತ ಹೇಳಿದ್ರೆ ನಿಮ್ಮ ಎಡಗೈನ ಮೂರು ಬೆರಳನ್ನ ನೀವು ಮ್ಯೂಚುಲಿ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಆಗಿರೋ ತರ 90 ಡಿಗ್ರಿಯಲ್ಲಿ ಬರೋ ತರ ಸ್ಟ್ರೆಚ್ ಮಾಡಿ ಹಿಡ್ಕೊಂಡ್ರೆ ಈ ರೀತಿ, ಇನ್ ಸಚ್ ಎ ವೇ ದಟ್ ನಿಮ್ಮ ತೋರು ಬೆರಳು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಯಾವ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಇದೆಯೋ ಅದನ್ನ ತೋರಿಸ್ಬೇಕು. ಸೊ ನಾವು ತಗೊಂಡಿರೋಂಥ ಕೇಸಲ್ಲಿ ದಿಸ್ ವಾಸ್ ದ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್, ದಿಸ್ ವಾಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ರೈಟ್? ಸೊ ನಿಮ್ಮ ತೋರು ಬೆರಳನ್ನ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇರುವಂತ ಡೈರೆಕ್ಷನ್ಗೆ ನೀವು ಸ್ಟ್ರೆಚ್ ಮಾಡಬೇಕು. ಅಂಡ್ ದ ಪಾರ್ಟಿಕಲ್ ವಾಸ್ ಮೂವಿಂಗ್ ಇನ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಡೈರೆಕ್ಷನ್, ದೇರ್ ಫೋರ್ ನಿಮ್ಮ ಮಧ್ಯದ ಬೆರಳು ಪಾರ್ಟಿಕಲ್ ಯಾವ ದಿಕ್ಕಿಗೆ ಮೂವ್ ಆಗ್ತಿದ್ಯೋ, ಮೋಷನ್ ಅಥವಾ ವೆಲಾಸಿಟಿ ಇರೋ ದಿಕ್ಕಿಗೆ ನೀವು ಮಧ್ಯದ ಬೆರಳನ್ನ ಇಟ್ರೆ, ಆಗ ನಿಮ್ಮ ಹೆಬ್ಬೆರಳು ಯಾವ ದಿಕ್ಕನ್ನ ತೋರಿಸುತ್ತೋ ದಟ್ ವಿಲ್ ಗಿವ್ ಯು ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್, ಡೈರೆಕ್ಷನ್ ಆಫ್ ದಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್. ಈ ಕೇಸಲ್ಲಿ ನಮ್ಮ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ರೂಲ್ ನ ಅಪ್ಲೈ ಮಾಡಿದಾಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ವಿಲ್ ಬಿ ಇನ್ ದಿ ಅಪ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್. Using the Fleming's left hand rule, the magnetic force on this particular charge will be upwards. What about if the charge is negative? ನಾನು ಒಂದು ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ತಗೊಂಡಾಗ ಏನಾಗುತ್ತೆ? Let me keep the other factors same. So this is the direction of the magnetic field. The negative charge is now moving in this particular direction V. Now, what will be the direction of magnetic force? Again, let us use the Fleming's left hand rule. So I'll get the same result. In this particular case, the thumb is showing upward direction. Therefore, the magnetic force must be in the upward direction. But Fleming's rule is applicable for positive charge. And for negative charge, we have to flip the direction. ನಾವು ರೈಟ್ ಹ್ಯಾಂಡ್ ಥಂಬ್ ರೂಲ್ ಇರ್ಬೋದು ಅಥವಾ ಫ್ಲೆಮಿಂಗ್ಸ್ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ರೂಲ್ನ ಕೋಟ್ ಮಾಡಿದಾಗ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ನ ಮೈಂಡಲ್ಲಿ ಇಟ್ಕೊಂಡು ಒಂದು ರೂಲ್ನ ಕೋಟ್ ಮಾಡಿರ್ತಾರೆ. ಹಾಗಾಗಿ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ನ ನೀವು ತಗೊಂಡಾಗ ಆ ಡೈರೆಕ್ಷನ್ನ ನಾವು ಆಪೋಸಿಟ್ ಆಗಿ ತಗೋಬೇಕಾಗತ್ತೆ. ದೇರ್ ಫೋರ್ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ಗೆ ಫೋರ್ಸ್ ಅಪ್ವರ್ಡ್ಸ್ ಇದ್ರೆ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ಗೆ ದ ಫೋರ್ಸ್ ಮಸ್ಟ್ ಬಿ ಇನ್ ದಿ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್. ಸೊ ದಿಸ್ ವಿಲ್ ಬಿ ದ direction of magnetic force in case of a negative charge. So this is how we can find out the direction of magnetic force which is acting on a moving charge which is moving in a uniform magnetic field. Okay, now let us move on to today's topic, which is origin of induced EMF in a conductor moving in a magnetic field. So we have a conductor here and we are saying it is moving in a magnetic field. So if a conductor moves in a magnetic field, what will happen to the conductor? So let us try to find out that. We have considered a conductor of length L, and we have placed the conductor in a magnetic field. Now I have considered the magnetic field to be entering into this plane, that is your screen, and the magnetic field is going into the screen. Therefore, we have represented it with this blue X marks. So this is the magnetic field which is entering the screen. Now, let me say the conductor is moving with some velocity v, which is at a direction perpendicular to the direction of magnetic field. So, ನಾವು ಒಂದು ಕಂಡಕ್ಟರ್ ತಗೊಂಡಿದ್ದೀವಿ, ಎಲ್ಲಷ್ಟು ಉದ್ದ ಇದೆ ಆ ಕಂಡಕ್ಟರು. ಆ ಕಂಡಕ್ಟರ್ ಏನಾಗ್ತಿದೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ಮೂವ್ ಮಾಡ್ತಾ ಇದೆ. ನಾವು ತಗೊಂತಿರುವಂಥ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನಾಗಿದೆ, ನಿಮ್ಮ ಸ್ಕ್ರೀನಿಗೆ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಆಗಿದೆ ಹಾಗೂ ಸ್ಕ್ರೀನಿನ ಒಳಗಡೆ ಹೋಗ್ತಾ ಇದೆ. So which is represented by this X mark. ಈಗ ಈ ಇಡೀ ಕಂಡಕ್ಟರ್ ಮೂವ್ ಆಗ್ತಿರೋದ್ರಿಂದ ಏನಾಗ್ತಾ ಇದೆ, we know if it is a conductor it will have free electrons, right? It will have free charges, which is the free electrons. When the whole conductor is moving to the right, each and every free electron is also moving towards the right. ಒಂದು ಕಂಡಕ್ಟರ್ ಅಲ್ಲಿ ಫ್ರೀ ಎಲೆಕ್ಟ್ರಾನ್ ಇರೋದ್ರಿಂದ ಇಡೀ ಕಂಡಕ್ಟರ್ ಮೂವ್ ಆದಾಗ ಏನಾಗುತ್ತೆ, ಅದರಲ್ಲಿ ಇರುವಂತ ಪ್ರತಿಯೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಕೂಡ ರೈಟ್ ಸೈಡ್ಗೆ ಮೂವ್ ಆಗ್ತಾ ಇದೆ. ಸೊ ವಿ ಹ್ಯಾವ್ ಕಮ್ ಟು ದ ಸೇಮ್ ಕಾನ್ಸೆಪ್ಟ್ ವೇರ್ ಅ ಚಾರ್ಜ್ ಪಾರ್ಟಿಕಲ್ ಇಸ್ ಮೂವಿಂಗ್ ಇನ್ ಅ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್. ಒಂದು ಚಾರ್ಜ್ ಪಾರ್ಟಿಕಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ಮೂವ್ ಆದಾಗ ಏನಾಗತ್ತೆ, ಅದ್ರ ಮೇಲೆ ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಬರುತ್ತೆ. ಇಲ್ಲೂ ಅದೇ ತರ, when the whole conductor is moving, each and every electron in it will experience a magnetic force. And how do you find out the magnetic force? We know the magnetic force is given by Q into V cross B. And how do you find out the direction of the magnetic force? We use the left hand thumb rule. So the magnetic field is into the plane. So that is represented by the forefinger. The middle finger gives you the direction of the velocity of the charge. Then the direction of the thumb should give you the direction of force. So if this is the B, let me write the axis. So X, Y, or let me call this as Z, and this is the Y axis. Magnetic field is in the Y axis, charges moving in the X axis. Therefore, the right hand thumb rule or the left hand rule, Fleming's left hand rule, both will give you the direction of the force as upwards. Now the charge is negative. If I take a negative charge, the direction must be opposite. Therefore, this will be the magnetic force. ಅಲ್ವಾ, ಒಂದು ಚಾರ್ಜು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ಮೂವ್ ಆಗ್ತಾ ಇದ್ರೆ ಅದ್ರ ಮೇಲೆ ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ಬೀಳುತ್ತೆ. ಫ್ಲೆಮಿಂಗ್ಸ್ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ರೂಲ್ ನ ಯೂಸ್ ಮಾಡಿದಾಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ಗೆ ಡೌನ್ವರ್ಡ್ಸ್ ಇರುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ದಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್. ದೇರ್ ಫೋರ್ ಆಲ್ ದಿ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಆರ್ pushed downwards. Each and every electron which is present in the conductor will now experience a force that will try to push the electron downwards. Therefore, all the negative charges will start accumulating at the bottom of the conductor or one side of the conductor. So, this side of the conductor is going to become negative. If one of the side becomes negative, what does that mean? If all the negative charge starts moving downwards, that is equivalent to all the positive charge moving upwards. ಅಲ್ವಾ, ಈ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೋರ್ಸ್ ಇಂದ ಪ್ರತಿಯೊಂದು ಎಲೆಕ್ಟ್ರಾನು ಡೌನ್ವರ್ಡ್ಸ್ ಮೂವ್ ಆಗಕ್ಕೆ ಶುರು ಆದ್ರೆ ಅದರ ಅರ್ಥ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಅಪ್ವರ್ಡ್ಸ್ ಮೂವ್ ಆಗ್ತಿದೆ ಅಂತ ನಾವು ಅಸ್ಯೂಮ್ ಮಾಡಬಹುದು. ಆಸ್ ಅ ರಿಸಲ್ಟ್, ದಿ ಅದರ್ ಸೈಡ್ ಆಫ್ ದಿ conductor will start accumulating positive charge. Therefore, we have created two poles. One of the side is polarized to positive charge. The other end of the conductor has been polarized to negative charge. What does that mean? Now, this will create an electric field, right? So, whenever the negative charge moves downwards, that will create an electric field. The electric field in this case will be pointing upwards. Now we have two forces. One is the magnetic force which is trying to pull the charge downward, and because of this accumulated charges, there is an electric field which is generated, and that generated electric field, I can write it as Q into E, right? Electric field is given by the formula Q into E, and the direction of the electric field is opposite to that of the magnetic field. So this is the magnetic field FM, and this is the electric field FE. Now at some particular point, we will reach a steady state. Steady state means the electric force will start balancing the magnetic force. Whenever the electric force balances the magnetic force, we will say we will reach the steady state. So the ends of the conductor now has a potential difference, or we can say an EMF is developed between the ends of the conductor ಅಂತ ನಾವು ಹೇಳಬಹುದು. ಸೊ ಈ ಇ ಎಮ್ ಎಫ್ ಎಷ್ಟು ಅನ್ನೋದನ್ನ ನಾವು ಈಗ ಕಂಡುಹಿಡಿತಾ ಇದ್ದೀವಿ. ಓಕೆ, ಸೊ ಲೆಟ್ ಅಸ್ ಫಸ್ಟ್ ಟ್ರೈ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ವಾಟ್ ಇಸ್ ಇ ಎಮ್ ಎಫ್. ಯು ಮಸ್ಟ್ ಬಿ ನೋಯಿಂಗ್ ಇ ಎಮ್ ಎಫ್. ಇ ಎಮ್ ಎಫ್ ಸ್ಟ್ಯಾಂಡ್ಸ್ ಫಾರ್ electromotive force. What is electromotive force? You must be knowing this. If there is a conductor, of course it will have electric charges. If there is no external circuit, or if there is no battery connected, what will happen to this electrons? They will be in random motion, and that will not produce any current, right? If the current has to flow in this conductor, what should you do? There must be a force that pushes all the electron in a particular direction. That particular force is called electromotive force. So how do you produce a force on this electrons? For that, what you will do is you will connect it to a battery, right? Once you connect this conductor to a battery, the battery is the source of EMF. Now each and every electron will experience a force, and a current starts flowing in this conductor. Or I can say we have created a potential difference between the ends of the conductor. So ಒಂದು ಕಂಡಕ್ಟರ್ನ ನಾವು ತಗೊಂಡಾಗ ಎಕ್ಸ್ಟರ್ನಲ್ ಬ್ಯಾಟ್ರಿ ಏನೂ ಇಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ಏನಾಗುತ್ತೆ, ಅದರಲ್ಲಿ ಇರೋ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಎಲ್ಲ ರ್ಯಾಂಡಮ್ ಆಗಿ ಮೂವ್ ಆಗ್ತಾ ಇರುತ್ತೆ. ಆ ರ್ಯಾಂಡಮ್ ಮೂವ್ಮೆಂಟ್ ಇಂದ ನಮ್ಗೆ ಯಾವುದೇ ಕರೆಂಟು ಬರೋದಿಲ್ಲ. ಸೊ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗ್ಬೇಕಂದ್ರೆ ಎಲ್ಲ ಎಲೆಕ್ಟ್ರಾನು ಇನ್ ಅ ಪರ್ಟಿಕ್ಯುಲರ್ ಡೈರೆಕ್ಷನ್ ಡ್ರಿಫ್ಟ್ ಆಗಬೇಕು. ಸೊ ಡ್ರಿಫ್ಟ್ ವೆಲಾಸಿಟಿನ ಕ್ರಿಯೇಟ್ ಮಾಡ್ಬೇಕಂದ್ರೆ we have to apply a force. ಆ ಫೋರ್ಸ್ ಅನ್ನ ನಾವು ಏನಂತ ಹೇಳ್ತೀವಿ? ಎಲೆಕ್ಟ್ರೋಮೋಟಿವ್ ಫೋರ್ಸ್. To make the current flow through this conductor, so to make the current flow through this conductor, there must be a force pushing the charges through this conductor. So this particular force is called as electromotive force. So we can produce that electromotive force by connecting it to a battery. So by the definition, we know that whenever there is no flow of current, if there is no external circuit, if there is no current, I can write EMF is equal to potential difference, right? ಇದು ನಮಗೆ ಗೊತ್ತಿರುತ್ತೆ. ಸೊ ಎಕ್ಸ್ಟರ್ನಲ್ ಸರ್ಕ್ಯೂಟ್ ಇಲ್ಲ ಅಥವಾ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗ್ತಿಲ್ಲ ಒಂದು ಸರ್ಕ್ಯೂಟ್ ಅಲ್ಲಿ ಅಂದ್ರೆ ಅವಾಗ ನಾವು ಇ ಎಂ ಎಫ್ ನ ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ಗೆ ಈಕ್ವಲ್ ಅಂತ ಬರಿಬಹುದು. ಸೊ ವಿ ಕ್ಯಾನ್ ರೈಟ್ ಇ ಎಂ ಎಫ್ ಇಸ್ ಈಕ್ವಲ್ ಟು potential difference. Potential difference is nothing but work done in moving a charge from one point to another point against the field. So you must be knowing the definition of potential difference. Therefore, it is work done per unit charge, right? So what is work done? The formula for work is force into displacement. So force into displacement divided by Q. Now using this, I can write the formula for EMF. So EMF can now be written as force. If I say the length of the conductor is L, and the displacement can be written as L now, divided by charge. But if you observe carefully, what is F by Q? F by Q is nothing but electric force per unit charge. We know that the electric force is given by charge into the electric field. Therefore, what will be F by Q? F by Q will give me the electric field. So let me replace this F by Q. The final formula for EMF will be equal to electric field into the displacement of the charge. So this is an important equation you must be knowing, and we are going to use this formula in our derivation. Okay, so this is the background of the derivation. Now let us actually derive the formula for EMF in a conductor moving in a magnetic field. ಈಗ ತಾನೇ ಹೇಳ್ದಂಗೆ ಒಂದು ಕಂಡಕ್ಟರ್ ಇದೆ, ಅದು it can be a wire or it can be a rod, and it is actually moving in the magnetic field, right? This is the magnetic field B, and the magnetic field is actually into the screen, and the conductor is moving with a velocity V towards the right, and it is moving in a direction perpendicular to its length. And since it is a conductor, it will have free electrons in it, and when the rod moves, each and every electron can be assumed to be moving towards the right with the same velocity V, right? So each and every electron will be moving in the same direction as the rod itself. Now we know that if a charge moves in a magnetic field, it will experience a magnetic force. Therefore, how do we write the magnetic force? Magnetic force Fm is given by charge into V cross B. Here we are taking the electron, therefore the charge of the electron is minus E. So I can write Fm as minus E into V cross B. And what about the direction? The direction is given by the Fleming's left hand rule, and we know that in this particular direction, because it is a negative charge, the direction of the magnetic field will be downwards. So there is a force which is trying to push all the electrons towards the end of the conductor. Say the end of the conductor, if I name the conductor as PQ, all the electrons are pushed towards the corner Q. And because of this, the side Q will develop a net negative charge, and the side P will develop a net positive charge. There is an electric field which is generated or set up inside the rod. If there is an electric field, it will lead to an electric force. So if the charge is present in the electric field, it will experience an electric force. So what will be the electric force? We know the electric force is given by Fe, which is equal to Q into E. In this case, charge is nothing but minus E for electron into the electric field. So what will be the direction of this force? Obviously, it will be upwards, right? And if you compare the two forces, electric force is actually opposite to the magnetic force. So both the electric force and the magnetic force are in opposite direction to each other. So this process will continue till a point is reached where the electric field starts balancing the magnetic field. So ಈ ತರ ಅಕ್ಯುಮುಲೇಷನ್ ಕಂಟಿನ್ಯೂ ಆಗ್ತಾನೆ ಇರುತ್ತೆ ಎಲ್ಲಿವರೆಗೂ ಅಂದ್ರೆ ಒಂದು ಸ್ಟಡಿ ಸ್ಟೇಟ್ ರೀಚ್ ಆಗೋವರೆಗೂ ಈ ಒಂದು ಪ್ರಾಸೆಸ್ ನಡೀತಾನೆ ಇರುತ್ತೆ. ಸೊ ಅಟ್ ದ ಸ್ಟಡಿ ಸ್ಟೇಟ್ we see magnetic force becomes equal to electric force, and now we can write minus E into E is equal to minus E into V cross B. So rest of it is only mathematical simplification. Let us see what happens now. So E and E gets cancelled, and we'll end up getting electric field is equal to V cross B, right? So we get a situation where a steady state is reached and the electric field becomes equal to V cross B, and I can also write this formula if I remove the vector notation, the magnitude of this can be written as E is equal to VB into sine theta, where theta is the angle between V and B. So it will be again 90° in this particular case. And as we just discussed now, because there is a potential difference between the two ends of the conductor, that will result in an EMF. Because there is a potential difference between the two ends of the conductor, I can say an EMF is generated across the rod, and the EMF is given by E is equal to electric field into the distance or the displacement of the charge. In this case it will be L. Now using equation number 3 here, in place of E, I can write E is equal to, or the EMF is equal to VB sine theta into L, or if I rearrange it, I can write this as VBL sine theta. So the EMF that is induced in a conductor moving in a magnetic field is given by the formula VBL sine theta, where L is the length of the conductor. What does that mean? ಒಂದು ಕಂಡಕ್ಟರ್ನ ನಾವು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ಮೂವ್ ಮಾಡಿದಾಗ ಆ ಕಂಡಕ್ಟರ್ ಅಲ್ಲಿ ಒಂದು EMF ಜನರೇಟ್ ಆಗ್ತಿದೆ. ದಟ್ ಮೀನ್ಸ್ ದಿಸ್ ಕಂಡಕ್ಟರ್ ಹ್ಯಾಸ್ ನೌ ಬಿಕಮ್ ಅ ಬ್ಯಾಟರಿ. Just look at this. What is this equation telling you? This conductor, which is now moving in a magnetic field, is actually behaving like a battery. You can have a battery, you can make your own battery. What you need is just a conductor and a magnetic field. If you just move that conductor in a magnetic field, you have created your own battery. Right? So that is the beauty of this equation, and this effect is coming because of the magnetic force which is acting on a moving charge. Okay, that is all for today. In the next class, I'll be discussing about a very interesting law called Ampere's law. So these are my references. Hope this session was useful. See you in the next class. Thank you.